Hi folks, as I promised in the previous episode, today I want to talk about a couple really weird things that I've bumped into when I was looking for some standard test suites for my hardware random number generator. And there were some really weird things going on there, let me tell you. Now, there are basically two suites that I'm using. The first one is called rng-test from the rng-tools from Linux. And the rng-tools, they're basically two components. One is a program called rng-test, which takes some hopefully random input and checks if it's really random, sort of. And the other one is called rng-d, the rng daemon, which takes blocks of random data, checks them, and then feeds them to the kernel as seed for the cryptographic pseudo-random number generator in there. And that thing was kind of weird. What happened? Well, let me show you. I've actually got about 5 gigabytes worth of test data here in my notebook. Not enough for the other one, but enough to show you a couple things. I've got a couple test files in there. I split them up in chunks of 16 megabytes, and so you see I have about 310 of these times 60 megabytes makes about 5 gigabytes. And if I use rng-test and feed it random out dot all zeros, takes a moment, and then disaster strikes. So out of the chunks of data it tested, which were 6,710, 6,705 worked out okay, and there were 5 failures. And there are effectively 5 tests. I've only seen a continuous run once or twice when I've been using 64 gigabyte worth of data from either Linux or FreeBSD random. So these are actually extremely rare, but the other ones actually do occur. And when I first saw this, I thought, okay, something's wrong, let's see if I can fix it. And the situation simply never changed. So what I can do as well is use a file random out, which is a concatenation of all the individual ones. So let me show you. So this is about almost 5 gigabytes in size, and I could actually run that through there. However, it's nice to see intermediate results. So we say every 1,000 tests it should give us an intermediate status, and there you see errors and more errors and heaps of errors. And yeah, it takes about 6 or 7 minutes to run this. So let me see what the eventual result looks like. Here we go. So we've got about 2 million tests and 1,600 failures. Scary. And that means the random number is broken, right? Well, actually not. And the key here is you have to read up how it works. There's this FIPS 140 standards. It's a NIST standard. NIST is the National Institute for Standardization and whatever. The people who published this NSA optimized pseudo-random number generator. And FIPS is Federal Information Processing Standard, which are a series of specifications they publish. And what happened here is that you have to actually check how this works. And this is where things already get weird. All these tests work by taking a 20,000 bit sample of random bits, run them through these tests, and then decide, okay, that block is good or not. And that means if you have a proper high quality random number generator, it will actually decide that some perfectly random data is no good and drop them, which will obviously bias the output of this sort of filter. Now, it might be reasonable if you feed this into the seed of a cryptographic pseudo-random number generator to still be okay. But, well, that's worth a closer look, right? And that's where things got even scarier. Because this standard that's mentioned even there in the output is FIPS 140-2. Now there's a draft for -3, so I decided to go for that. Didn't find anything. Okay, back to 140-2. Yeah, the tests were there. They were defined, but there were no explanations why they were defined like this, why they set whatever thresholds, and there was no mention of that this should actually only be used to, for example, a cryptographic random number generator or pseudo random number generator, because the output is actually biased. Oh, by the way, it didn't give any information of how many failures to expect from a proper random noise. So what I did was take dev-urandom on both Linux and FreeBSD, run that through there and get an idea of how many failures to expect. And the tests there, hang on, what I've learned was you should expect about 1 monobit error in 10,000, about 1 poker test in 10,000. So in this case, monobit is a bit high, poker is a bit low, but probably still within reason. And runs and long runs are about 3 per 10,000, which work out reasonably well at this point. Run is a bit high, and continuous run hardly ever occurs at all. So this is what I found out, but it wasn't documented anywhere, which is systematically wrong in my opinion, because it's this sort of it's okay until somebody proves that it's broken. And that again is what leads to these situations. Oh my god, what is it? Somebody do something, our crypto stuff is broken. And we have the problem with cryptographic algorithms, which are considered secure despite some theoretical attacks, until somebody actually shows up and says, okay, I've broken it. And then there's general panic. And until then, everybody's laughing about these theoretical attacks. So what I'd expect from something like this was an explanation why these algorithms, why these thresholds, and what to expect from them and what not to expect from them. And in a case like this, where they drop perfectly random data and in effect bias the output, where to use or not to use it. Didn't do that. And then something else happened. The names of these tests seemed somehow familiar. And yes, I found them. About 20 years ago, when I was a graduate student, I've been working on hashing functions, among other things. Not cryptographic hashes, but things used for randomized algorithms and that sort of stuff. And yeah, I'd seen at least the names of these tests. And guess where? Won't believe it. Yeah. Art of Computer Programming, Donald Knuth, Volume 2, Semi-Numerical Algorithms. There's a huge chapter on random number generators in there. Not cryptographic ones, but ordinary ones. And in there, a couple of tests were defined. Now, first off, this book was first published, first edition, which I don't have, 1969. So this stuff is 40 years old. Second, the tests in here are not for real randomness, let alone cryptographically strong randomness, but for algorithmic pseudo-random number generators, not really meant for cryptographic purposes. And the FIP standard uses them. So that's weird. And then, of course, there's still the question, why have they been removed in the -3 draft? No explanation given. They're just removed. No replacement, no nothing. Just gone. So, I'm probably paranoid. I mean, should be part of my job. But this sounded just plain wrong. And then something else happened as well. On Bruce Schneier's homepage I found a paper, or a link to a paper. I've been starting to read it. I've been carrying it around with me for some time, so it's getting a bit worn, but well, you can find it on the web, print it again if you want to. Apparently from last year, security analysis of pseudo-random number generators with input, def-random, is not robust. And more specifically, what they're talking about is def-random and def-random on Linux. Haven't fully read it. I admit I am not really familiar with this sort of math. I guess I found a mistake in there actually. Harmless one, but kind of a mathematical typo. And the end result is that, well, you can actually sneak stuff into the Linux kernel through these tests to manipulate the seed of the pseudo-random number generator. And that's scary. It's for kernel 3.7.8, so might not be a problem anymore because somebody fixed it, but no good. Okay, so I'm actually using this test because it's pretty fast, and now I know how many errors to expect and what ratio between the different kinds of errors, but I found that pretty disappointing. Now, the other test I found is called Dieharder. It's basically a rewrite of a pretty old suite called Dieharder. And Dieharder is already, the release shipping with Debian is from 2003, so 11 years old, roundabout. And you can tell, you can definitely tell. It's single-threaded. Well, 10 years ago, most computers only had a single core CPU, so that sort of made sense, but these days it just slows things down. And it's aimed at pseudo-random number generators, not even necessarily cryptographic ones, but general ones. And it's using some of these tests used in Knuth and a lot more, and it works reasonably nice, just has one problem. Well, it has a couple of problems, but biggest problem is for full run of the standard tests needs about 15 or 16 gigabytes worth of data. Means about 10 days of the generator producing random number random bits day in, day out. So it makes testing rather slow. That's why I'm still using the RNG test. And yeah, I found a couple of funny things that I can't quite explain. For example, if you tell it, okay, do tests on a smaller set, and because you only have a few megabytes worth of test data, it apparently needs more data. Really weird. Can't quite figure out what's going on there. The description of the algorithms is, well, can't say that I understand all the details. So again, it's a documentation thing. I mean, I'd be fine if there were links to some sort of technical papers where the algorithms were actually properly explained and analyzed and whatnot, but that's missing. So that's not exactly nice. And what's worse, if you tell it to just read the input over and over again for some tests just fail dramatically because they are meant to detect that things are repeating. So not really the most helpful. Makes things really tedious to use this, but right now it's the best independent test I could find. So, and it takes about 2 hours or so to run, an hour or two on that machine. Could be significantly faster if it was to be, it could be run in parallel, but okay. Yeah, but I'm not even going to show you those things. They're just, actually, let me show you. I've got a couple things prepared here. Now let's get rid of this stuff. So, yeah, that looks good. So, if you run it like this, Dieharder -G201, which means use random number generator 201, which actually means read input, because this stuff is designed for pseudo-random number generators. So you have to select the pseudo-random number generator you'd compile in. And with those, generating a couple gigabytes worth of data is not a problem. With real hardware random number generator, it is. You tell it which file to use, and then you say -A. -A means do all standard tests. And this is basically the output that you get. Starts here. So input file was around 3 times, and a couple of things pass, and then there's some weak ones which have been rewound a couple of times, and it counts the total number of times it had to rewind the input file, because it's not starting from the beginning with every new test. And you see there are tests failing, and some are weak, blah 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 blah, some other fail, and you don't really know what to make out of it. So that's what you just run it with the minimum parameters. So next thing you do is you give it a longer file, which is in this case was random out, which is still too small, but it gets less rewinds. And you see a lot of more tests have passed. Some are still weak. Weak means you want to test with a bigger test set, so you might need more than 16 gigabytes. You should have about 1 test in 100 giving you a weak result, and 1 in 10,000 should actually fail when everything is okay. And yeah, and you see I need plenty more of data. So the next thing you do is read the man page and find out if you invoke it like this. So you use a large file, do all tests, y-1 tells it to start from the beginning of the input file with every single test. No, hang on. -y1 means test until you're sure if things are okay or if they failed. So if a test shows up as weak, it just gets run with more data until the entire thing is resolved. -K2 is something you have to do with -y1, because there are different ways to do the statistic tests and whatnot. You find the details on the main page, and -S1 says start from the beginning of the file for every single test. And then you get output like this. So they're all looking pretty good. Then here's one that's actually weak, and the p samples means basically the number of test results are taken, and then they do another statistical test over those. So we go to 200, and then the results are okay. And then we see one. This one is actually pretty annoying. It needs lots of data, so the file has to be rewound again. And if you do 2 or 3 rewinds, they inevitably fail. So the output generally looks pretty good. There's the bit distance tests. They sometimes show up as weak. And there's some weak stuff. So basically what happens, every time one of these shows up as weak, we double or we add another 100 to these p samples, and after that the test is okay. That's still a bit surprising that we have these so often, but okay. And these RGB lagged sum tests. RGB are the initials of the author, Robert G. Brown. Robert G. Brown. These lagged sum tests, they are quite interesting, and they need so much data we start to rewind things here again, which means I actually have to go through the entire stuff. Otherwise the tests have passed. So at this point I'm reasonably confident that this stuff is actually okay. But I want to do some more testing. Yeah. So and there's another good one here. Hang on. Basically, if you want to know what the tests are, or which tests they are, do Dieharder -L for lists, and then it shows you tests do not use or suspect, and still they are run with all the, when you request it to run all tests, there is no such thing like run all sensible tests, which I find a bit disappointing. And if you want to know more about what the tests are, you Dieharder -D, which one should we try? 17-H, and you get an explanation, kind of what it's doing. It's not on the main page, you just have to read these things. And yeah, it's okay, but these explanations are fairly short, and I'd really like to see some more information, possibly as a reference to some technical paper or whatever. So yeah, I'll use it for my testing, but it's not something I'm really happy about. But at least this stuff seems to be reasonably clean. Other problem, of course, is it's 11 years old, and I've got one cryptography book, Bruce Schneier's Applied Cryptography, and I've been taking a look in there about random number generators and whatnot. That book's about 10 years old, and in there random numbers are just not a problem, not really. And these days we know they are. So the last 10 years a lot of things have changed, and these tests are not for cryptographically strong randomness. So looks like I'll have to do some of this stuff myself after all. And actually I've been doing some programming there. Started off with a little framework to read whatever input I get at whatever speed it comes in, and then let algorithms loose on it to see if the input is actually correct. And right now the only test I've so far implemented is I tell it, okay, I want to test if the bit bias is no more than so and so many ppm, parts per million. And I've checked that I'm at less than 10 ppm with a confidence of 6 sigma, so that's 3.4 errors in a million or so, which is pretty much industry standard for these, or for pretty much all quality test stuff. And problem is, if I want to go from 10 ppm to 1 ppm, I need 100 times as much test data. And even for 10 ppm, I need in excess of 10 gigabytes already. So still working on that. And I'll still need lots of test data. I can't help it. So I keep that thing generating noise data all the time. And by the way, sometime last week, I actually had a block of data which was broken. All zeros, all ones. I'm not even sure which one it was. And I'm not entirely sure what happened, because I am using the von Neumann extractor, so that actually shouldn't happen. Something really strange has been going on. So I'll generate a couple more tens of gigabytes and see if it happens again. My guess is that something went wrong on the serial interface. Probably the best explanation for that. Or somebody tampered with the FTDI chip here already. So I already had some visitors from the NSA here while I was making a bit of a living every once in a while. So that's the situation. Found that quite surprising, but well, basically means, if nothing else, hopefully from this project there will be some test suites coming out that other people might use to build their own hardware random number generators. And that's cool. Okay, so much about this stuff today. And as usual, if you want to discuss, if you have suggestions, if you have ideas where I could find some other tests, please come over to the forum at www.stepladder-it.com/BIVBlog/29. If you watched this on YouTube and think you liked it, you could do me a favor and give it a thumbs up, as usual. Oh, and in case you haven't read the t-shirt in its entirety, because I've been sitting a bit low, there you go. And that's really about IPv6 generally, but actually it applies to this stuff as well. Don't trust it because it worked yesterday. So that's it for today. Hope you enjoyed it, and hopefully see you again probably in a week or so. Bye.